Moving on. Today we are going to get into some more sorting concepts. We just finished, and if you remember back in 161, we did a combination of searching and looked at different ways to search, including just a straight linear and then a binary search. And then after that, we got into some sorting things. And in the sorting, we did we discussed three different types, and you even wrote a program for me that had like four or five different sorts in it, including the dam sort. But the three different types, the first one was called the selection sort. And just a quick review of how it worked. What if I take an array of like, I'm going to take an array of 12 numbers, cut that in half, cut that in thirds, cut that in thirds, and each one of these in half. And I'm going to fill it with numbers like 10, 4, 8, 11, 6, 2, 9. I don't want to repeat any here. 15, 13, 1, 7, and 20. And the way the selection sort worked was I went through this whole thing and until I found the smallest. And right now I'm looking at starting at this location, and I say, okay, I got 10. Is there something smaller than 10? Yes. So I'm going to keep track of 4. Is there something smaller than 4? No, 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 no. Yes. I want to keep track of 2. Is there something smaller than 2? And you get out here and go, oh, yeah, there it is. The 1. The 1 is going to be smaller. And if you watch the videos, you got this. And I just want to briefly touch on these because I think today is a lesson where I teach it more than just covering it. But the reminding of the selection sort was, oh no, I went to here and I found a smaller one. And I said, okay, we're going to swap those. I needed to keep track, but I went through and then I moved on to the second space. That went all the way out. So right now, if the size is 12, I'm gonna have, and this is, coming back to what we've been talking about. I got this whole big O notation, and for this guy, the big O would be, well, let's see. I started at 0. I had a loop from 0 to, I wanted to go here and compare them all the way out. Okay, so in my, this is 0 up here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I wanted to compare 0 to the rest, would be my first loop. So 0, 2, in this case, 11. My second loop would be this guy, and let's, if I called him counter sub 1, then this guy, counter sub 2, he would go from 1 to, oh, no, wait a minute. He would go from 1 to 11. This guy would go from 1 to 10 because eventually I'm going to be comparing 1 to 0 with 1 through 11. 2, and again, this, my apologies, that should be counter 1 to 11. So, the old school of 0, 1, dot, 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 all the way down to the 10th spot, because eventually I'm going to be comparing 10 and 11. 0 down to 10, 1 to 10, and so on and so on. Excuse me, 11. And then 10 to 11 at the end. Hope I didn't confuse you. This would be big O what? Well, the way it looks, it's going to be 2 loops.
Is it n squared?
Excellent. N squared. Yeah, N squared. And of course, when we were doing these loops, we had the ever popular swap, and it looks something like int ampersand A, int ampersand B. Excuse me, asterisk. the reference variables. Second sort, and we did a couple of these, was the exchange sort. And this was a little different. And instead of waiting till the end and making a swap, this did immediate swaps. It would interchange pairs right away. And this, of course, was the one that was the like the Dan sort and and the bubble sort. And if I looked at this same list up here, we would say, okay, as we go through, if it's smaller, swap. And yes, there's a swap and so forth and so forth and so forth. And then if there was a swap, I would do it again. So I would have something like, while there's a swap, I'm going to get in here and go in a loop for counter equals 0 to size -1. So I would compare, 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 compare. And if there was a swap, I'd do it again. Okay, but I was exchanging those side by side pairs. And one bubble sort made it so that everything moved to the front from lowest to highest. The other one took the largest to the end. And then finally, there was a third one that we didn't get into that we will get into next Monday. And that was called the insertion sort. And that was the one that was like a deck of cards. And that was if I took an array, first number went in was 10. Second number was 4. I made it 4 and 10. I inserted it where it's supposed to go. The third number was 8, bigger than 4. It's less than 10. I now had an array. Oh, man, I'm so sorry. An array that looks something like this. Okay. So it was sorting it as I was putting it in, just like you would see with a deck of cards. Okay. The good one today. And yeah, I like this one. The one today is something, and it's called a heap sort. Hopefully you watch the videos. Hopefully some of you are going, yes, I actually got it from the videos. I feel pretty good about it. Instead of doing a hands-on, no, I want to make sure we all get this. And in order to do a heap sort, first thing we have to do is build a heap. That's not a beep. That's a heap. Heap, and build a heap. Okay. As we go through, you're going to see that we're going to, this heap is a new data type. And, according to my notes, it is big O n log n. And, the timing of why we started big O when we did was to get it going. So you have a little idea of when I say, oh, this is big O n squared or big O n log n. You're starting to see some differences and understand that this could be a faster type of sort. All right. Why do we wait for heap sort? Well, we need to work with a binary tree. Binary tree. And we remember a binary tree has a left, a node, and a right concept. Okay. There's two choices, left or right, binary, 0 or 1 or the other. Let's see, the binary tree has to be complete. And we did a definition of complete the other day, and that was filled top to bottom, left to right. And it has to fill this second criteria, which is going to be a little funky from what we've been doing. And the new thing that comes into play is the parent is greater than the children. And you're going to see this is a little different than what the binary tree was. The binary tree, the smaller child was to the left and something larger than the node was to the right. This isn't exactly the same. Let's see a couple of examples. What do we have? And the notes I'm going to just show you instead of drawing it. Is this a heap? Is it filled in top to bottom, left to right? Yes. So
Yeah.
it is complete. Is every parent greater than its children? Yes. This guy is not complete. It's missing one there. This guy, the parent is not larger than the node. Now, if I could move that guy up and bring the 6 down, I'd have a heap and I'd be happy because I'm happy. Clap along. No, settle down. Okay, I'd be happy. But this is not. I need this guy to move up. And when we start talking about moving up, and this comes from a coffee term, we need to be able to percolate up. And conversely, we're going to be doing something called percolate down. Now, this is really a bizarre one because in order to do these heaps, we're going to be thinking with a binary tree to make the concepts make sense, but we're going to be doing with an array. So we're going to be thinking with a binary tree, and this is just one from up above. And we came over here. This was 2, this was 4, and this was 3. And we were all happy with this. We said, yes, that fits the definition of a heap. And we're going to be thinking of this, though, as an array and working with it that way. 9, 8, 4, 6, 2, 3, 0, 1, 2, 3, 4, 5. So we're going to be thinking of it as a binary tree, but working with it as an array. And the other day we said, oh, if I have a parent, its children are at, where are the children?
Is it 2n
I'm
minus
at
1?
1, which is 8. One's children were at 3 and 4. So there's going to be 2 of them. What were the formulas?
Is it 2n plus 1
Yep, that was one of them.
and 2n plus 2?
You got it. And then if I'm a child, my wife calls me that all the time, where is my parent? And we had a formula for that. So in order to move around in this array, if I'm looking at 4 and I want to know where its parent is, well, location 4's parent is 1, and we had a formula for that. N minus 1, integer division with 2. Okay, questions? All right, let's get ready to work with the heap. Work all week long. Any questions? All right, so if I take a heap, and again, as soon as we learned a new data type, that's that's how you erase my home whiteboard. We know a new data type heap, and we want to take a look at its functions. All right. Oh, I always check is empty. We're going to be working with an array. I don't know if I'm going to need is full or not. These are question marks. We've been doing insert, pushes, and all those different names, and we've been doing deletes. Yeah, that would be a good question. Every data type we learn, what are different words for adding an element to that data type? We used insert, we used push, we used NQ, we used quite a few different ones over the semester. All right, I'm going to need something to get largest. Somehow or other, I need to get the largest. And where would the largest be?
Isn't it in the last spot?
It would be like array element 0 or the root or the head or the top, all those different names for a linked list or for an array. But I would say at sub 0 since we're thinking about that. And somehow I need to move the largest. And again, I don't know if I need all these and exactly what I'm doing and so forth, but and then we're going to have two more percolate up. I don't know what that is, and perk down. And again, I don't know if I need all these, but I've gotten to the point where every time I learn about a new data type, I'm going, should I, could I, do I need one, and so forth. Right. The bottom line is we are sorting. This is a heap sort. We are sorting. We've been doing some searching. We're doing sortings again. Today and next week, we're doing sorting. All right, so I want to build a heap, and I'm going to do something like, and the first one we're going to do is take a look at this, removing the largest. Now, I want to end up with a sorted list. If I know my largest, if I know my largest is at the top, why would I want to remove it? If I know my largest, 77 is at the top, 60, 41, 15, 55, and 35. And again, this is sitting in a nice array, 77, 60, 41, 15, 55, and 35. My end goal is to have a sorted list. So if this is my biggest number, where would I like it to end up going?
The end.
At the end. And when I put it at the end, that means this guy's got to go somewhere. So this guy's then going to move 35 to the front. So inevitably, I'm going to say, hey, I want to switch those. So now 35 is up at the top, 60, 41, 15, and 55. And this guy down here is now going to be 77, but we're going to pretend he no longer exists. Okay, so now I do have my last number at the end, and so forth and so forth. Well, what would I like to happen now? Well, I'd like to repeat that process and looking at all the blues, be able to put the next largest number beside the 77. But I don't have the next largest up here, do I? No. Okay, so this guy, once I move that 35, I create something called a semi-heap, where it's really, really close. It's just off a little, just a little bit off. And what do I need to do? Well, however this works, but I need to percolate down so that it becomes another heap. Now, how do I percolate down? Well, I'm going to say, what's the biggest of the two numbers? Well, this 35's got to go. So he's going to switch with 60. So the first thing is I'm going to have 60 now up top, 35, which is like my key number, 41, 5, 55. So we're just kind of ignoring that 70. That's not very nice and clean. And how did I know where to check? I checked out where's my children. Is this smaller than this? Well, first of all, which one of these is which direction would I go? In this case, smaller than both, but I want to swap it with the 60. Redo. Can I percolate down more? The answer is yes. I'm going to switch 35 and 55. So now I have 60, 55, 5 didn't go anywhere, but 35 is now over here. So I did the swap from here to here. I did a percolate from here to here and do it again. Make the swap. Put 60 down here at the end. 35 would go up. Now I'm ignoring 60 and I'm deciding which way is that 35 going to go. Yeah, code for that. Hopefully that's interesting code. Okay, so I took care of get largest. Is empty. Whatever I have, I would check my array sub 0 equals whatever I'm putting in there by default. What might I put in there by default? Depends on what this list is. Is this the list of temperatures? Well, then I would fill the array with, maybe fill it. Do I need to fill it with something? Could I have a size variable that says size equals 0? So then I'm looking, it is empty. Is full, oh boy, that's going to come into play when I'm filling this, something I'd have to check. I looked at your programs and I had some wild numbers for my prime number. Remember, we were using a prime number for our hash function. I had a couple that weren't prime, and I had some as high as 57. And it depends on how many items we're working with, but there were some reasonable ones like 19 and 23 that I think worked pretty well. And a lot of you did a great job making that a constant variable at the beginning of your program. Okay, so I'm at this world right here. When we sat down, I gave you this list. I gave you a heap. So now I have to figure out, well, wait a minute. We already said we needed to percolate down. We needed to move the largest. Moving the largest wasn't that hard. It was swapping this with whatever my new end one is. Okay, so we have array size. That's not very good. We have a count. We would need that to be some sort of number. And we were talking about that to be 0. Array size might be 10. We might need like a working count of how many I'm working with. Here I was working with 6. Now I'm only working with 5. Okay, so that's helping me check is empty, is full. And when we're doing this sorting, we're never really ever going to delete anything. So I need to talk about these two yet, the insert and the percolate up. Okay, so let's take a look at inserting an item. And one way to insert is to add an item to the end. To the end and percolate up. Which, if you think about percolate down, how did we do that? Well, we checked it, both children, found the largest one. If it was bigger, we swapped them. Percolate up is going to be the same kind of deal. So let's see what I have. I'm going to start with 60. 60. The next number I'm going to add is 55. Not too bad, right? Complete. And it still matches at the parent greater than the child. 41. Okay, this isn't very exciting. 15. Going to keep it simple this first time. Still good. 35. Uh-oh. 50. Nope, this isn't a heap. So I need to percolate up. How am I percolating up? I'm checking the array values and saying, uh-oh, we need to swap them. I'm checking the array values. Checking 50 and it's and I'm going to have to switch those. 50, 41. I percolated up. Keep going. Is it greater than 60? No. So now I would stop. 60, 55, 50, 15, 35. What do we have down here? 41. What if I added 100? Check its parent, swap them. Check its parent, swap them. Should end up looking something like this. Okay, so inserting an item, the idea is we're trying to fill a heap. And when I'm done, heap is done. Heap is ready. Now let's talk about this. I inserted 65. I inserted 55. I might have to percolate up. I inserted 41. I might have to percolate up. I inserted 15. I may have to percolate up 2 levels. So there's a lot of checking and percolating that would be going on in order to get this heap ready to do the heap sort. Well, a second method is going to be, I'm going to take that same list of numbers, 60, 55, 41, 15, 35, 50, and 100, and I'm going to, instead of adding and checking, I'm going to add them all first. So up here we did add and check. Here we're going to add all, then check. Okay. So let's see, we're going to add all 60, 55, 41, 15, 35, 50, 100. Okay. Up here, we did our percolate up. So the first method of getting it ready, and again, all we're doing is getting it ready so that we can go and now do the heap sort. Now we can start everything we need to do to sort them. But with the second way, we added them all. And now we're going to check, but this time we're going to check at the go to lowest parent and perk down this time. The last one up there, we did a percolate up. We're going to go to the lowest parent. The lowest parent is 41. I'm going to percolate down. Can it go down? Yes. It can swap with 100. 141. Now I go to the next parent, 55, and I percolate down. I don't have to. Then I go to the last parent and percolate down. Well, in this case, it only switches with 100. So now this becomes 100, this becomes 60, and in percolating down, I would keep going until I would find blanks or something, some way to stop. And just like that, I have a heap. So two different methods. Add an item to the end and percolate up if need be. Otherwise, fill the heap, put all the values in the array, go to this parent. And again, you see why it's easier to look at as a linked list and then work with it as an array. I'm going to put you in groups. You are going to make a heap with the list of numbers 1, 15, 30, 8, 100, 16, and 2. You're going to make a heap. You're going to do method number 1 and method number 2. Method number 1 was add a number, then perk up. Method 2 was add all, go to last parent, and then percolate down. I don't know if you can do it well with the whiteboard. That's probably the best thing. But I want you to call me into your group and show me your solution. And that will be it then for today.